Hello. Now, today we're going to look at geometric series, and we've already looked at geometric sequences, where we have a list of numbers, and to get between each of the numbers in the list, we have to multiply by our common ratio, OR. So we've already dealt with that. Now we're going to deal with the series, which is where we're adding up those terms instead of just listing them. So we're going to be using this formula here, and it's on page 22 in your log tables as normal. The key thing we want to note in terms of using this formula, a very common error when putting this into the calculator, is the power on our common ratio, the little n here, is just on our common ratio. An extremely common error is that people will write in their common ratio, put the bracket, and then put the power of n, which would end up putting the power of n on this entire bracket on the top line, which is not what we want. So just be careful when you're putting into the calculator that you're putting the power on the common ratio only. It's a very common error that costs people quite a bit of marks. Now, let's put this into practice. If we have a series like this, and it keeps on going, I want to find the nth term and the sum of n, or the sum to n, I should say. So everything we already know about geometric sequences still holds. We're just now dealing with our series as well. We're going to add up our terms. So let's find Tn first. Well, if I'm given this, I may not be told I'm dealing with a geometric situation. How do I recognize that I'm dealing with a geometric situation? I can see that I am dividing by 3 each time, or I'm multiplying by a third, depending on the way that you want to put it. So, I am multiplying by a third each time. Now, I can just see that with these numbers. But if I couldn't see it, what would I do? Well, I can see that there's no consistent common difference. So I could start checking the common difference, the second difference, the third difference, so on, and see if they were constant. And I can also check for my common ratio. So my common ratio is Tn all over Tn minus 1. So we can pick any two terms, any two consecutive terms, and divide them by each other, and we will get the same number if we've got a geometric pattern. So if I'm dividing by a fraction, what does that mean? It means that I'm going to end up flipping the fraction I'm dividing by upside down, flipping the third upside down and turning it into multiply. And then I have 3 over 9 is a third. But just so we're clear, we could have put a third over 1, which is straightforwardly just a third as well. So we can see that the ratio of any two consecutive terms is the same. This is the defining characteristic of a geometric pattern. So I know that my common ratio is a third. The other piece of information I need for my formulas is going to be the first term, which is just straightforwardly 1. So I'm looking for Tn, and on page 22 in my log tables, I read off that that is a times or to the n minus 1. I have my a and my or found. If I wasn't sure of what to do, I'd go to page 22, write that down, and see if I could figure out my a and my or. And now I am going to just sub in. So I know that a is 1. I know that or is a third. N minus 1. So I just end up with the 1 multiplied in has no effect, so I just end up with 1 to the power of n minus 1 all over 3 to the power of n minus 1. 1 to the power of anything is just 1, so I end up with 1 all over 3 to the power of n minus 1, and this is what gives me my values for Tn. So this is the nth term of my pattern. We're already familiar with that. Now let's do the same type of work for S of n. So we write down our formula from our log tables, being careful with how we write it in. We sub in And these can get quite messy because we're dealing with fractions on top of fractions. So be careful with your brackets here. Our common ratio is a third to the power of n all over 1 minus a third. So the multiplied by 1 here has no effect, and we end up with 1 minus 1 to the power of n all over 3 to the power of n. Our power in our bracket, just like here, becomes a power on each of the terms inside. So we multiply by the power on the bracket. We multiply our powers by the power in the bracket. And then 1 minus a third is 2/3. I am again dividing by a fraction. So I end up flipping that over to multiply. 1 to the power of anything is 1, so that becomes 1 over 3 to the power of n on 3 over 2, I should say. I flip the fraction upside down and multiply, or invert and multiply. And it's a little bit up to you in this case how much you tidy that up, but S of n, broadly speaking, will be 3 all over 2 minus 3 all over 2 on 3 to the power of n. And that's as far as we need to go. If we were asked for a particular value of S of n, for the sum to the 10th term or something like that, we just sub in 10 for n. Now, based on our work with limits the last day, we have a particular thing that we want to talk about. If I have a sequence like this that it is getting smaller and smaller down to 0, specifically if or my common ratio is less than 1. So if my common ratio, or the absolute value of my common ratio, is less than 1, like a third is less than 1, then I would have a series of terms that is getting smaller and smaller, eventually tending down towards 0 as n gets larger and larger and larger. These numbers are going to get smaller and smaller and smaller as n gets larger and larger and larger. So what effect is that going to have on our series, on our sum to n? Well, if we have the sum to n here, if or is a number less than 1 and we take it to a very large power, what's going to happen? Well, we will end up with a fraction to a large power, which is going to get really, really, really small. It is effectively going to tend down to 0. So if or is less than 1, if the absolute value of or is less than 1, then as n tends to infinity, or to the power of n is going to tend to 0. If or is a fraction is a smaller number than 1. If we imagine that or was equal to a tenth, this becomes fairly easy to see. Or to the power of n would be equal to 1 over 10 to the power of n. This would get absolutely tiny as n got large. So what effect does that have if we have the sum to infinity, where we set n to be getting larger and larger and larger? So our or to the n is going to get smaller and smaller and smaller. So we end up with a on 1 minus 0, effectively, all over 1 minus or. So we end up with the formula a all over 1 minus or. And this is actually on page 22 in your logbooks as well. Even though it's pretty easy to derive, they give it to you in the bottom of page 22. So this is our formula for the sum to infinity. It is extremely important that you keep this very clear in your head when you are looking at whether you can use this sum to infinity or not. This is only true if or is less than 1, so that our terms would tend towards 0, like we talked about when we were doing the limits to infinity the last day. So let's put this in practice. If I have a series like this, or a sequence like this, 12, 6, 3, continuing on. So this is our sequence, but what would the sum to infinity of this pattern be? Well, let's write down what we know. We have A would just be equal to 12, or is equal to Tn all over, or Tn minus 1. Any two terms divided, any two consecutive terms divided, so it's going to be 3 all over 6 is equal to a half. Or just a reminder, we could have done 6 all over 12 would also give us a half. They all would give us a half. So we have or would be equal to a half. A is equal to 12. So the sum to infinity I can use, because or is a half, which is less than 1. The absolute value of or is less than 1. Or the modulus of or is less than 1. So I sub in to my formula, and I get 12 all over 1 minus a half is equal to 12 all over a half is equal to 12 on 2 over 1 is equal to 24. What does that mean in practice? It means if I added up all of the terms in this list, and they are going to keep on going to infinity. So we're going to keep dividing by 2 each time. So the next term in here is going to be 3 all over, or 2. The next term is going to be 3 all over 4. That series, that sequence I should say, keeps going on forever. But the numbers keep getting smaller and smaller and smaller. And so they matter less and less and less to the overall sum of all of the terms together. So in practice, what we find is that it actually all adds up to exactly 24. And if you're interested in more advanced mathematics, it was an open question in maths for a long time as to whether that sum genuinely added up to exactly 24 or it just got really close to 24. But we would say mathematically that it actually equals 24 in a fairly meaningful sense. But in practice, if you're asked about a sum that keeps on going, so if we kept doing this forever, or if the pattern continued, or if we're to sum to infinity, there are lots of different ways an exam paper could ask you to use the sum to infinity. But if we recognize that we're using a sum to infinity and our common ratio is less than 1, or the absolute value is less than 1, then we can just use this fairly straightforward formula and we can get an exact value for the sum of an infinite number of terms, which is kind of a funny idea, but does work out mathematically. So that's what we need for the beginning of geometric series.